I'm going to start over. Okay. So, so I'm going to start today with the chapter 8 and section 8.1, which is Lewis dot symbols. Okay. And we can think of Lewis dot symbols as being connected to the idea of valence electrons. So the valence electrons are the outermost electrons in the atom. But we can also think of it in terms of ions as well. So in either the atom or the ion. Okay. The core electrons are the inner electrons. These are the ones closer to the nucleus. Okay. Now, the valence electrons are the ones that are involved in bonding. So those are the ones we're going to focus on. We're not concerned as much with the core electrons. So here's what you can do. If you take the periodic table, you can find the number of valence electrons in the atom just based on the position in the periodic table. So if it's in group 1A, it has 1 electron. Oops. Okay, so 1. So group 1A has 1 valence electron. If it's in group 2A, it has 2 valence electrons. Oops. Okay. Then ignore the transition metals, ignore the D block. We don't have to worry about those. So then go straight to 3A. So 3A is boron and aluminum. And then 4A is carbon and silicon. And then 5A is nitrogen and phosphorus. And then 6A is oxygen, sulfur. 7A is your fluorine and chlorine. And then 8A is the neon and argon. And it works for the whole column. Okay, I'm just putting a couple of elements for the 3A and 4A because generally those are the only ones we're worried about. Okay, so that's the number of valence electrons right there. Very simple. Okay, just be careful. Make sure you have the periodic table that doesn't go 1 through 18. Make sure you have the one that goes 1A, 2A, 3A, 4A, so forth. Now, here's how we do this. You take the number of valence electrons in the atom, and then you draw the symbol for the atom, for the element, like H, for example, is hydrogen, and then you just draw a dot. So if it has 1 valence electron, you draw 1 dot, and that dot now represents the electron. So let's say, for example, we're going to do fluorine. Fluorine has 7 valence electrons. So what I'm going to do with fluorine is I'm going to start on the right side, 1, and then I'm going to go clockwise and draw 1 dot. And then once you get around, think of it like a square, like a box. Once you get to 4 sides, then go back to where you started, 5, 6, 7. So there's your 7 valence electrons, okay? So you're going around this way. There's no reason you have to go around that way, but that's just one way to do it, okay? So 1 dot on each side of a square. And then once you get up to 4, if there's more electrons, then start pairing the electrons. So notice this Lewis dot symbol has paired electrons. These are paired electrons, right? Remember what we said about electrons? They're spin up, spin down. When you have 2 together like that, that means that they're paired. If you have 1 like this all by itself, then this is an unpaired electron. Okay, so these are called Lewis dot symbols, right? And we're going to use this sort of this symbolism, these symbols, in order to kind of talk about chemical bonding. Now, you can also do it for ions. And so let me show you how you deal with that. So again, these are the the dot symbols we're talking about right now. Lewis was the one who came up with this idea. Okay, Lewis dot symbols. So for example, let's say we want to do fluoride, F minus. We want to draw the Lewis dot symbol for F minus. How do we deal with that? Well, F minus, what is F minus? F minus is the same thing as a fluorine atom plus a negative charge, which means it has one extra electron, an extra one, right? That's what makes it fluoride as opposed to fluorine. It has an extra electron. So what you do is you say, okay, fluorine has 7 valence electrons. It has one extra electron. So you add one more, and now you have 8 valence electrons. Okay, so fluoride has 8, fluorine has 7. Okay, so how do we deal with that? Well, what you do is you draw the symbol and you do the same thing. You just go around clockwise. 1, 2, 3, 4. And then you form pairs, 5, 6, 7, 8. And so just to indicate to people that it's charged, we put a little bracket on the side and then write the negative charge there. So this would be the Lewis symbol, the Lewis dot symbol for the fluoride ion. Notice how it's different than the fluorine atom? The only way that it's different is it has one extra electron, right? Fluoride. So let me show you an example from Alex. Okay. So draw the Lewis dot diagram. They call it Lewis dot diagram. Typically we call it Lewis dot symbols, but they call it Lewis dot diagram for the oxide ion. Okay, so draw the Lewis dot diagram for the O negative ion. Okay, so here's what you do. You first look up the symbol, so that's oxygen. Oxygen is in group 6A. So what that tells you is it has 6 valence electrons, right? So you got 6 valence electrons. And then it's negative. It has the negative charge. So you add one more. So that gives you 7 valence electrons. If it were -2, you would add 2 more electrons and you'd have 8. Okay, so now you got 7. So you take the symbol O and then you just start drawing in dots. Go clockwise. 1, 2, 3, 4, 5, 6, 7, right? I'm going to stop right there. We're at 7. And then since it is negatively charged, you draw a little bracket and you put a negative there. Okay, so that would be the O negative anion or O negative ion. That would be its Lewis dot symbol or its Lewis dot diagram, okay, for an ion. What happens if you have something that's positively charged? So what about we want to draw the Lewis dot diagram for AS plus? Okay, now it's positively charged. What do we do with its positive? Remember from this discussion of redox chemistry, when you gain electrons, you become negative. When you lose electrons, you become positive. So this means that we lost 1 electron. Okay, so what you do is you say, okay, let's look and see where arsenic is. Arsenic is underneath phosphorus. It's in group 5A. So that means it has 5 valence electrons, but it's positively charged. So that means we lost 1 electron. So now we have just, so this would have 5 electrons. This one's only going to have 4 electrons. So you just take 1 electron off. If it was +2, you would take 2 electrons off. If it was +3, you would take 3 electrons off. So we have 4. So you just draw the symbol and then 1, 2, 3, and 4. So there's your, oh, but it's positive. So, right, so you got to put a little bracket here and then you put a plus. Okay. So not all of them are ions when you do these problems. Some of them are neutral. So it'll tell you if it's neutral. So let's do it for a neutral atom of bromine. Okay, bromine. So bromine is in group 7A. Okay, so that means it has 7 valence electrons. It's neutral, so there's no adding or subtracting electrons. So 1, 2, 3, 4, 5, 6, 7. And there you go. There's no need to put brackets around this one because it's not an ion. You only put the bracket if it's positively charged or negatively charged. Okay, so those are called Lewis dot diagrams or Lewis dot symbols. And we're going to use those to start our discussion of chemical bonding. And it's based on the following idea. What happens in chemical bonding is we can think of bonding as having 2 forms. The first type is what we call ionic bonding. Ionic bonding is relatively simple. It's the attraction of ions. And in a way, it's analogous to the structure of the atom. The atom has protons at the center in the nucleus, and then there are electrons that are negatively charged outside. So that attraction of the atom gives it stability. The same is true for an ionic compound. So imagine if you have something like sodium chloride. Sodium chloride is actually comprised not of atoms, but of ions. The sodium is positively charged and the chloride is negatively charged. So what's happening is this. The sodium, let's take a look at our position in the periodic table. Sodium is in group 1A. That means it has 1 valence electron. But notice it's positively charged. So what does that mean? That means it lost an electron. So the sodium doesn't have any valence electrons, right? So it's actually 0 valence electrons. Now let's do the chloride. Chlorine is in group 7A, right? That means it has 7 valence electrons, but it's negatively charged. So what does that mean? That means it has 8, not 7, but 8 valence electrons because it's negatively charged. Okay, so chlorine has 7, but chloride has 8. Sodium has 1, but the sodium ion has 0, right? It's lost an electron, it doesn't have any valence electrons. So what happens is you end up with this interesting dynamic. You have these 2 ions that are just attracted to each other because they have opposite charges. That's what pulls them together. But you also have this interesting situation where one of them doesn't have any valence electrons, and the other one has 8. So what do you notice about that? If you add up, so I'm putting a negative here. Notice I put the brackets on the opposite side for the sodium, just to kind of show you. The attraction is just because they're opposite charges. That's what holds them together. But the other thing we notice here is that if you add up the valence electrons between the 2 of them, 0 plus 8, you get 8. And so many ionic compounds have this phenomenon where if you add up the valence electrons for the 2 ions, it adds up to 8. It's a common number that appears. Sodium chloride being an example of that, okay? So that's ionic bonding, and we can use these Lewis dot symbols to represent the valence electrons that exist in them. We're not going to spend much time on that. We're mostly going to focus on the second type of bonding, which is called covalent. Covalent is more complicated and in a sense more interesting. This is caused by the sharing of electrons by different atoms. But we're going to see that this number 8 appears to be important, at least at times. It appears to be important in covalent bonding as well. So this is the sharing of electrons. So let me show you an example of this. Let's take, for example, oxygen, O2. Okay, oxygen is the molecule. It's not a compound, right? Because it only has one element, oxygen, but it is a, it is a molecule. So that means there's some sort of chemical bonding taking place. So the question is, what is the bonding that's taking place? Well, oxygen is in group 6A, so it has 6 valence electrons, right? And it's 2 oxygens. So what I'm going to do is I'm going to draw the Lewis dot diagrams or Lewis dot symbols for each of the 2 atoms, right? So I'm showing one over here and one over here. So I'm going to go 1, 2, 3, 4, 5, 6. And then I'm going to do the same thing here. 1, 2, 3, 4, 5, 6. So each of them has 6 valence electrons. So far, okay, that's fine. Here's what we're going to suggest happens. We have a sharing of electrons. So the way I'm going to represent this is I'm going to suggest that these 2 electrons here, one from each atom, is going to be shared by the 2 atoms. And that these 2 electrons are also going to be shared between the 2 atoms. Okay, so there's 2 pairs of electrons getting shared. Now, to do this, I'm going to have to move some of these dots around just to make it work out. So these 2 are now shared. So I'm going to draw them like this. And these 2 are shared. So I'm going to draw them like that. Right? So I'm drawing them in between the 2 symbols. Then we have 1, 2, 3, 4. So I'm going to show them as pairs. And then we've got these 4 over here, and I'm going to show them as pairs. Okay, now notice I drew those pairs on the top of the symbols and on to the side. That's perfectly fine. You could also have drawn a pair up here and a pair down here, or a pair up here and a pair down there. There's no real requirement where you draw those pairs. The point, though, is that they will form pairs. And notice we have even numbers of electrons here, okay? So what we're going to do is we're going to claim that these 2 pairs are called bonding pairs. So we have 2 bonding pairs. These 2 right here and these 2 right here. Each atom used 2 of its electrons, 2 of its valence electrons, to form these new pairs, which are called bonding pairs. And we're going to talk more about what those bonding pairs are later. But for right now, we're going to claim that they're shared by the 2 atoms. And so we have 2 bonding pairs. One here and the other one there. Each atom also has 2 non-bonding pairs. Okay, so we have a total of 4 non-bonding pairs. 1, 2, 3, 4. Okay, 2 of them, of course, are on each atom. So now notice what we're doing. We're calling electrons bonding pairs, which means they're holding the atoms together like a glue. And there are non-bonding pairs, which are not holding the atoms together. They're isolated on specific atoms. They're not shared between the 2 atoms. Now, typically what we do, I'm going to draw this again. typically what we do is we represent these bonding pairs with a line, with a straight line, typically horizontal, but it could also be vertical. So we represent it like this. A straight line is meant to represent these two dots at the top here. And a straight line is meant to represent these two dots here. So this right there is representing that. And then this is being boy, what happened there? This is being represented here, that straight line there. And then we represent the dots that are non-bonding like this. Okay. This is called line notation, and this is much more common than this one over here. Sometimes you'll see this, but this is a more common method of representing the bonding that's taking place. Okay, so remember, each of those lines represents 2 electrons, not 1 electron, but 2. Okay. You will also, if you look this up online, you will also see that it's not uncommon to represent the non-bonding pairs with another line like this. See how I'm representing that? These little lines here represent 2 electrons. So this pair right there is represented with a line. That's typically a more advanced method, and it's not universal. Organic chemists will use that sort of notation. When you do general chemistry, you're not likely to see this in the textbook. You're more likely to see this. Alex also shows this. Some of the problems show this. So these 2 notations you should be aware of. So what you'll see, so for example, let me show you. Here's a Lewis structure. For this one, let's count the bonding pairs and non-bonding pairs. Okay, let's count them, okay? Well, the bonding pairs are the ones in between the atoms, in between the 2 atoms. So there's one there, there's a second one, and then there's a third one. So it looks like we have 3 bonding pairs. And then the non-bonding pairs are the ones that are not in between the atoms. They're only on one of the atoms. So it looks like there's 2 non-bonding pairs. Okay. So that molecule N2, dinitrogen, has 3 bonding pairs and 2 non-bonding pairs. And there is another term that's used for non-bonding pairs. It's also called lone pairs. It's the same meaning. So a lone pair is only on one atom, so it's alone. It's not connected to the 2 atoms. We can also use the line notation. In line notation, you're going to represent the bonding pairs with a straight line. So we have 3 bonding pairs, so we have 3 lines. And then the non-bonding pairs will represent them as pairs of dots. So notice there's a tendency to represent these as pairs. We can connect that to our discussion back in chapter 6 with this idea, right, that electrons have a tendency to form pairs. Right? They form pairs. So we're representing those pairs, spin up, spin down, with these 2 dots or with the line notation, right? Those are pairs of electrons. Okay. Now, what I want to do is start doing some counting here. So as I said, remember we talked about sodium chloride, that there was, if you added up the valence electrons, they came out to 8, and that number comes up quite a bit. We're going to notice that with these 2 molecules, O2 and N2, the same phenomenon occurs. So let me show, I'm going to redraw them. I'm going to redraw O2. I'm going to use the line notation. I prefer line notation. And now here's what I'm going to do. For each atom, count the number of electrons surrounding its symbol. Okay, so for each atom, so let's take this oxygen atom over here on the left. How many electrons does it have surrounding it? Okay, I'm going to start over here. Well, you got 2 right there, right? So that's 2. Here's another 2, so that's 4. Here's another 2, so that's 6. Here's another 2, that's 8. So that oxygen on the left has 8 electrons. Okay, so I'm going to write it this way. This one has 8. Okay. Now let's do the oxygen on the right. We're just counting up the electrons around it. So it has 2 here at the top, 2 here. And then it also has the 2 and the other 2 in the bonds, right? So we're counting those twice because we're doing it for each atom. So that oxygen atom on the right also has 8. So they both have 8. Now it's true, 4 of them are being shared, right? The 2 pairs in the middle, the bonding pairs, are shared. So what has happened effectively is that by sharing these 4 electrons, each atom now has 8. And we could ask ourselves, why would that happen? Why is 8 such an important number? And here's what I'm going to do. I'm going to come back to oxygen. Okay, that's the electronic configuration of oxygen. It has 8 electrons, but remember, the 1s has 2 electrons in it, so that's filled. The 2s has 2 electrons, so it's filled. But the 2p, it only has 4. Okay, remember, oxygen is element number 8 in the periodic table. Okay. So there, oops, sorry, I drew that wrong. Let me do that correctly. 1, 2, 3, 4. Okay, so there's oxygen. That's the ground state configuration of oxygen. If you take a look at oxygen. I'm going to change the color here so you can see it. See how these 2 orbitals only have 1 electron in them? That's Hund's rule. There's room for 2 more electrons in there. So what happens? Effectively is the other atom, it has 2 electrons that it can share with the oxygen on the left. So let's do the other oxygen. The other oxygen, this one over here on the right, it also is 1s2, 2s2, 2p4. One, 2, 3, 4. So notice here, it has room for 2 electrons also. Both of them have room for 2 electrons. So here's what happens. This atom on the left has 2 electrons. This one on the right has 2. They share all 4. By sharing all 4, these 4 electrons now give you a total of 8 in this second shell, right? Because each of them already has 2 here. Each of them already has 4 here and 4 here. So that's 6 valence electrons. But by sharing these 4 here, they now each have 8. And we call that the octet rule. The octet rule is this idea that atoms become stable by sharing electrons such that they possess 8 valence electrons. The sharing is what gives them 8. Okay, remember, oxygen only has 6 valence electrons. It's in group 6A. But by sharing these 4 electrons, it now has 8, effectively. Both oxygens, that's the case. So what about nitrogen? I'll do this on another slide. Nitrogen, let's consider the Lewis structure for nitrogen. So nitrogen is in group 5A. So it has 5 valence electrons, right? So it doesn't have 8, it only has 5. What that tells us is if you could give it 3 more electrons, it might be stable because now it would have 8. That's the octet rule. That's what we observe. So here's what happens. You take another nitrogen, which has 1, 2, 3, 4, 5. This one also has 5 electrons, 5 valence electrons. So if they can share electrons, right? So we're going to have them share 6 electrons. So what I've done is I've moved this one here, and this one over here. So those are those 3. These 2 are still over here on the right. And then I've moved this one over here, this one over here, and this one over here. And then these 2 are coming over to the side here. Okay. So now look what happens. Now they're sharing 6 electrons. They each have 2 on the outside. So what does that do? That gives each of them 8 electrons. We can represent that with the line notation too. 6 electrons shared between the 2 atoms. 2 electrons not shared. So each one now has a total of 8. And again, that's our octet rule. So what we observe is that molecules, many of them, tend to form structures in which the atoms, oh, let's do a different one than this one, sorry. In which the atoms share electrons such that they have 8 valence electrons. So here's an example. Notice I'm using the line notation. This is called Cf4, Carbon Tetrafluoride. Let's analyze the structure here. This carbon is sharing electrons with this fluorine, so there's 2. It's sharing electrons with the other fluorine on the right side, so there's 2. It's sharing electrons with this fluorine down at the bottom, so that's 2. And it's, oops, sorry. Gosh, that's a terrible typo. Put a carbon over there. And it's sharing 2 electrons with this fluorine on the left side. So that's a total of 8 electrons, right? That carbon now has 8. But keep in mind, carbon is in group 4A. It only has 4 valence electrons. So what has happened? It's sharing the electrons with the fluorine, and now it has 8. Likewise, fluorine is in group 7A. It has 7 valence electrons. But in these Lewis structures, it has a total of 8. Right? By forming a bond to the carbon, it now has 8. So this 8 comes up a lot. Again, it has to do with the 2s and the 2p. There's a maximum of 8 electrons you can fit in there. But the atoms don't have 8. They only have 4 or 7 or 5, or in the case of oxygen, 6. So they form bonds to other atoms to get up to 8. That sharing of electrons is what gives them 8. That's the octet rule. Now, there is a phenomenon which is similar for hydrogen, but it's not 8, it's 2. So hydrogen is unique. It's actually unique in the periodic table. And the reason it's unique is because hydrogen is in the first row, right? It's element number 1. So it only has one orbital with electrons in it, and that's the 1s. So what happens if you give it one more electron? So I'll draw this a different color. If you give it another electron, that shell is now filled. It only needs one electron to get up to 2 to fill up that entire shell. So instead of it needing 8 electrons, it only needs 2. And we call that the duet rule. Duet meaning 2. So you got the octet rule for the other elements, but you got the duet rule for hydrogen. So hydrogen then doesn't tend to share enough electrons to give it 8. It shares enough electrons just to give it 2. So this is methane, which is CH4. Take a look at this one. This hydrogen only has 2 electrons. So does this one. So does this one. So does this one. 2 electrons, right? Each bond is 2 electrons. Okay. So duet rule for hydrogen. So what's observed is when you look at these Lewis structures or these Lewis symbols and all of this, there's a tendency for most of the elements to try to get to 8 by sharing, but hydrogen only tries to get to 2 by sharing. So it will only have a bond. So you would know immediately this is not a possible structure. This one's not possible. Why? Because if you show 2 bonds to hydrogen, that's 4 electrons. And that's not possible, right? Hydrogen is going to have a maximum of 2 electrons. Okay. Likewise, if you see a structure like this, okay, I can tell you right now, this is not possible either, because take a look at this carbon. It has 2 electrons here, and it has 8 electrons there, right? That's 10 electrons. 10 is not possible for carbon. We're going to max out at 8. That's our octet rule. So it turns out these little simple rules, 2 for hydrogen, 8 for carbon, 8 for nitrogen, it actually seems to line up with reality. When we actually look at the bonding that takes place in atoms, it appears to be this octet rule is the maximum number of electrons that these atoms can have. And so that allows us to very simply figure out some of these Lewis structures. So let me show you an example. Okay, I'll do that one. Okay. Okay, so this is predicting the compound formed by 2 main group elements. Okay, so what they're going to do is they're going to give you 2 elements, sodium and barium. And then they're going to ask you, is it ionic, molecular, or neither? Okay, then they're going to ask you for the chemical formula. Okay, so there's 2 things you have to do for this one. You have to figure out whether it's going to form a compound, and if it does, is it molecular or ionic? And then let me do another one. And then you have to figure out what the formula is. So carbon and iodine. So again, is it ionic? Is it molecular? Is it neither? And then what's the formula? And then the third one is sulfur and barium. So ionic, molecular, and neither. And then if so, it's got a formula. Okay, so let's take a look at this one. So these are the main group elements. Okay, so let's take the first one. So sodium is in group 1A. Okay, that tells us it's a metal, right? The first two columns are metals. Barium is in group 2A. So that's another metal, okay? So here's what we'll say about this. What is observed is that ionic compounds are formed from a metal with a non-metal. Okay, that's what gives you an ion, like sodium chloride. Metal is sodium, chlorine is non-metal. So that means this is not an ionic compound. It has two metals, not a metal with a non-metal. So you know it's not ionic. Molecular compounds are formed from non-metals with non-metals. Oxygen with nitrogen, chlorine with fluorine, nitrogen with nitrogen. So that means that this substance cannot be a molecular compound either, because it's two metals. So you can check that off as not possible either. So this one is neither. And what that means then is it's not a compound. If it's not ionic and it's not molecular, it's neither. So sodium and barium don't form a compound, so there's no formula. There is no formula to go in there. Okay. Let's take a look at this one with carbon and iodine. Carbon and iodine. Okay, well, where's carbon? Carbon is in group 4A. So that means it's a non-metal, right? The metals are over here on the left side. We're ignoring the transition metals here in the middle. And then the non-metals are on the right side. So we have in column 4A, we have carbon, that's a non-metal. And then we have iodine, which is in group 7A. So that's two non-metals. Non-metal with a non-metal is molecular. Okay. Now, if it's molecular, here's what you do. You want to do the Lewis structure for the substance. So I'm going to make a little room here. Let me just save this one. And let me make a little room here. So we're going to do carbon and iodine. Okay. It's an interesting problem. So carbon is in group 4A. So that means it has 4 valence electrons. Iodine is in group 7A. So that means it has 7 valence electrons. Okay. So we're going to ask the question, how many electrons does carbon need to get up to 8? And how many electrons does iodine need to get up to 8? Okay, it's not going to be the same number, right? So carbon needs 4 electrons to get up to 8. Iodine only needs 1 electron to get up to 8, right? So it's 4 and 8. So here's what we do. Okay. The iodine already has 7. So it only needs 1 more electron. So how do we deal with that? What we do is we say, hey, if it just needs 1 more electron, then it just needs 1 from the carbon. It just needs 1 bond to a carbon, okay? But the carbon, it needs 4 electrons. And when it shares an electron with the iodine, I'll draw these two bigger just so you can see that those are the two that are being shared. That only gives it 1 more electron. So that gives it 5, right? So what do? Well, here's the 4 that it has, 1, 2, 3, 4. By forming a bond to iodine, that gives it 5, but it needs 3 more. So here's what happens. It forms a bond with another iodine. So that gives it 6. And it forms a bond with a third iodine. and that gives it 7. And it forms a bond with a 4th iodine, which gives it 8. Okay, so each iodine only needs 1 electron. That was this number here. So it only needs to form 1 bond. So the iodine is going to form a bond to the carbon, but the carbon needs 4 electrons. So it's going to have to form a bond to 4 separate iodines. So what's our formula then? We have 1 carbon and we have 4 iodines. 1, 2, 3, and 4. So that would be your chemical formula right there for Ci4. Okay, let me save this one. Okay, so Ci4. Okay, now let's try the third one, sulfur and barium. So we check and see where sulfur is. Sulfur is in group 6A. Barium, group 2A. So what is that? That's a metal with a non-metal, right? Metal. So metal with a non-metal is ionic. Okay. Now, how do we figure out the formula for this one? Let's make a little room over here. Okay, so we have sulfur and barium. Here's the way I would recommend this. If you have an ionic compound, the easiest way to do this is to go back to what we learned early in chemistry, which is that if something is in group 1A, it has a charge of +1. That's the easiest way to do it. If it's in group 2A, it has a charge of +2. Oops, I did it again. Okay, if it's in group 2A, it has a charge of +2. So that means barium is going to have a charge of +2. If it's in group 6A or 7A, it has a charge of -1 and -2. Okay, so sulfur is in group 6A, so it's -2. Okay, so now what we're going to do is we're going to draw the empirical formula. This is covered way back at the beginning of chemistry. What you do is you say, okay, this one's +2, this one's -2. So they're going to combine in a 1-to-1 ratio. Why? They have the same charges. They're both 2. So that means it's a 1-to-1. So it's just going to be BAS. Okay. So notice these are very different types of problems, even within one type of problem. So when we solve this one, we approach this one very differently. Molecular compounds are dealt with very differently than ionic compounds. Ionic compounds, you just have to figure out what their charges are and combine them. But with molecular compounds, you have to deal with the number of valence electrons. So let me show you another one. This one's a pretty complicated problem. So let me show you another one. Okay, we're going to do nitrogen and bromine. And then again, we want to know whether it's ionic, molecular, or neither. And then we're going to get the chemical formula. So we have nitrogen, bromine. Let's do that one first. We'll do this one first, and then we'll go on to the next one. Okay. So first step, figure out where they are on the periodic table. This is nitrogen. That's group 5A. That's a non-metal. Bromine is in group 7A. That's a non-metal. Non-metal, non-metal is molecular. So we know it's a molecular compound now. Okay. If it's a molecular compound, you're going to have to deal with the valence electrons. So here's what you do. You got nitrogen. Nitrogen has 5 valence electrons. So how many bonds does it need to get up to 8? It needs 3 bonds to get up to 8. Okay. What that tells you is that the nitrogen is going to be bonded to 3 different bromines. 3 bonds will give it a total of 8 electrons. Because it has 5, give it 3, it now has 8. So that tells you right there that the nitrogen needs 3 bromines. Each bromine gives it an extra electron because you're sharing the 2 electrons. Now, what about the perspective of the bromine? Well, the bromine has 7 electrons. Right? So bromine is 7. It only needs 1 bond to get up to 8. It only needs 1 electron, so it only needs 1 bond. So it actually works out, right? The bromine is bonded to nitrogen, it has 1 bond. This bromine is bonded to nitrogen, 1 bond. This bromine is nitrogen, 1 bond. So the nitrogen needs 3 bromines to get up to 8, but each bromine only needs 1 nitrogen to get up to 8. So our chemical formula then is 1 nitrogen and 3 bromines. So that one's pretty straightforward. Let's see what the second one is. The second one is barium and cesium. Okay. Well, barium is in group 2A. So that means it's a metal. Cesium is in group 1A. So that means it's a metal. So if it's a metal and a metal, it's not ionic because ionic is metal with nonmetal. It's not molecular because molecular is nonmetal with a nonmetal. So that means it's neither. So you might ask, well, if it's neither, what is it? And it turns out it's a mixture. It turns out if you mix metals together, you get something called an amalgam. So if you've been in the dentist's office, they don't use this anymore, I guess. But those of us that are older, our fillings are made out of what is called a Mercury Amalgam. Now they use I guess they use porcelain now or ceramic. But in the old days, we would use metals. So what you would have is a mixture of mercury and a different metal. I forget what they use, zinc or something like that. So they would mix those 2 metals together and it makes a liquid. It makes a solution. It actually makes a mixture. And so that's what a metal with a metal would be. It would be a mixture. Okay, so you don't have to worry about the chemical formula because it's a mixture. There is no chemical formula for a mixture. And then last one is lithium and oxygen. Okay, well, let's see what those are. This is in group 1A, so that's a metal. This is in group 6A, so that's a nonmetal, right? So if it's a metal with a nonmetal, that's ionic, right? Metal with nonmetal is ionic. Okay, so how do we deal with those? Then again, you go back to the periodic table. If it's in group 1A, it's +1. If it's in group 6A, it's -2. So now you have lithium, which is +1, and oxygen, which is -2. So how are those going to form? Well, in order to balance the charge, each +1 balances one of the negative ones. So you need 2 of the lithiums, right? 2 times +1 is +2, but you only have 1 -2 to give you -2. You're trying to balance those 2 charges. So that means you need 2 of the lithiums. So we write that as Li2, 2 lithiums, O, 1 oxygen. So Li2O. Okay. Let me show you one more. Next one is Krypton and Neon. Oh, this is a tricky one. Krypton and Neon. It's testing my what I'm telling you. Hydrogen and fluorine. and then nitrogen and iodine. Okay, so let's go through this one here. Okay, krypton, well, guess what? Krypton is in groups 8A, so it is a non-metal. And neon is also in group A, so it's also a non-metal. So okay, well, that must be a molecular substance. But keep in mind, these are noble gases. And what do we remember about noble gases? They don't react with each other, right? So it's just a mixture. So it's neither. So that's a little tricky there. They're both non-metals, so you would think that would be a molecular substance, but they're mixtures because it's noble gases. Noble gases essentially don't form compounds. If it's neither, there's no formula. So let's do hydrogen and fluorine. Now, hydrogen and fluorine is a very interesting substance. So you could get this one wrong very easily. Is it ionic? Is it molecular? Or is it neither? So even though hydrogen is in group 1A, like lithium, sodium, potassium, iodine, and sodium, potassium, rubidium, and cesium, even though it's in group 1A, it is considered a non-metal. Okay. Fluorine is in group 7A. It is definitely a non-metal. Okay. So both of them are non-metals. So that means it's molecular. Okay. Now, here's the trick with hydrogen. Hydrogen's the trick. We talked about it a little bit earlier. Hydrogen has one valence electron, but it doesn't need to get up to 8, right? It only needs to get up to 2. It's the non-metals that need to get up to 8, but hydrogen only needs to get up to 2. So it only needs 1 electron. So that means it only needs 1 bond. So that means hydrogen is just going to be bonded to 1 fluorine. It's not going to need more than 1 because it only needs 1 electron. Now, what about fluorine? Fluorine has 7 valence electrons. So it already has 7. It only needs 1 to get up to 8. So if it only needs 1 electron, it only needs 1 hydrogen. It only needs to form 1 bond. So each of them only need 1. So that means your formula is going to be HF. Okay. So molecular. What about this one? Nitrogen is in group 5A. So that's a non-metal. Iodine is in group 7A. So that's a non-metal. Okay. So that means it's going to be molecular. Okay. So how do we deal with this? Well, let's try nitrogen. Nitrogen has 5 electrons. It's a non-metal, so it needs 3 to get up to 8. Okay, so that means the nitrogen is going to have to form a bond with 3 of the iodines. Right? 3 iodines will give it 8. 2, 4, 6, 8. Okay. Now, what about the iodine? You don't even need to really worry about the iodine because they have to be internally consistent. Iodine is a group 7A, so it has 7. So it only needs 1 bond to get up to 8. And that's exactly what happens. The iodine needs 1 nitrogen to get up to 8. So there you go. Ni3. 1 nitrogen, 3 iodines. Okay. There you go. So we'll talk more about this tomorrow. Tomorrow is actually a holiday. So if you can't join tomorrow, that's fine. But I will, I'll do the lecture nonetheless. This one, I'm going to try to upload it to the Zoom website. It shouldn't be a problem. I'll post the link on Blackboard. But essentially what happened was my computer ran out of memory, so it can no longer store these recordings to it anymore. So I'm going to record this to the cloud, so it should become available. But I'll put the link on Blackboard later today. And then in terms of yesterday's lecture, I will try to see if I can get that uploaded somehow. It's just a technical glitch with the memory. So we'll see. What we've done is we've covered a little bit of what's called covalent bonding, which is section 8.3. But we're going to do a couple more because that section has something like 5 different types of problems in it. And then we'll get into electronegativity and then drawing Lewis structures. Okay, so we have a ways to go with this chapter. It's a big, long chapter, but it's actually the last of our big, long chapters. Okay, So have a great day, and I will talk to you later.
Thank you, Professor.
Thank you.
Bye-bye.